of the definite integral and go back to something we actually talked about before. This is going to be a section entitled the average value of a function, and the first part will be average or mean value of continuous function. But we've seen this before, as you may recall. We had the mean value theorem for integrals a while back, and here's what it said. I wanted to just have this written here for you to read. Remember, if we had a continuous function on a closed interval, then there's at least one point in that closed interval, call it x star, such that this equation holds, which is to say the definite integral equals f at x star times b minus a. And the term here on the right can be interpreted as the area of a rectangle, and we refer to f of x star as the average value, or mean value if you like, average value of f. So here's what we meant by a picture, so you can remind yourself of what that was. We had some sort of a function f of x like this, going from some point A here to some point B here. Then what this theorem says is that if you're trying to find the area under this curve, and you're trying to do it by finding a rectangle that has exactly this area and has this base, then you know if you took one down here it would be too small. If you took one up here it would be too large. But if you took one somewhere in the middle, at the very correct place here, which would be x star, whatever that place is, then the area under that rectangle, or the area of that rectangle, would equal the area under the curve. The continuity of the function makes this happen. So that's what we meant by having an average value or an average height here for the function, because this is f of x star. Now what I want to do here is show you another way that you can prove to yourself that this is the average value of the function, in a way that really connects up with what you already know about average values. So here's another motivation. And this is a very nice development. All right, let's partition our closed interval AB into n equal subintervals. We've done that before. So here we go. So that means the width of any one of the subintervals, which we've called delta x, is just 1/n of the total distance b minus a. Now, for algebraic purposes later, let me also note that if I solve for the 1 over n here, meaning I can solve and get delta x over b minus a, and I'll use that below. Now, here's the part where the motivation really begins. Let us, as we've done before, choose any points whatsoever, and we'll call them x1 star, x2 star, all the way up to xn star in the subintervals that we chose above. Now let's consider these n numbers. Consider the n numbers which are the functional values of those. So that would be f of x1 star, f of x2 star, and so on up to f of xn star. Now, if you had n numbers like this, imagine there were n grades. How would you find your average grade? Well, what you do is you'd add these n numbers up and divide by n. Well, we're going to do that here with these numbers. So let me write out what we're doing here. This is the average of n values of, so this is exactly n values of f in that interval AB. Now that, as I just said, is 1 over n times the sum of these numbers. So f of x1 star up to f of xn star. Now, 1 over n, as you saw above, can be written as delta x over b minus a. So let's put that in here. So this is delta x over b minus a, the same sum here, up to f of xn star. Then I'm going to leave the 1 over b minus a part. I'm going to take the delta x and push it all the way through. And then I'll use my summation notation to write this in a more compact form. So this will be 1 over b minus a times the sum from k equals 1 to n of the f of x k stars, where the k goes from 1 to n, you see, times delta x, which is the same for all of them. Now this should look very familiar, because if I let n go to infinity, because these are equal subintervals after all, then what I get out of this is 1 over b minus a, which stays out front, and then this part is exactly the definition of the definite integral from a to b of f of x dx. And this now can be interpreted in the same way as the average of, instead of just n values that we chose arbitrarily, in a sense this is an average of all values of f on or in AB. So we've gone from n to all, infinitely many, and we've found a way to define what it means to be an average value. And this number here is now what we're going to call the average value of the function. And this exactly corresponds to what we did above. So let's write that out here. Definition: if you have a function and you want to know its average or mean value, so the average or mean value of a function f, which is continuous, that's important here, on a closed interval AB. So the average or mean value of f is what we just discovered, and we can use a notation something like this. F sub AV for average. There are various ways this could be written. And that's just going to be 1 over b minus a, just the definite integral of f of x dx from a to b. So this number here is the average value of the function over the interval here AB. Simple as that. Now let me connect this up to something you've seen before. And I hope that this is a little surprising and satisfying at the same time. Remember when we talked about average velocity? That was the difference of positions at two different times, like s of t1 minus s of t naught, over the difference in the time, t1 minus t naught. So distance per time, it's like miles per hour or meters per second. That gave us average velocity. Now let's work with this a little bit. Let me pull the 1 over t1 minus t naught out front. And then I can interpret the top as s of t evaluated from t naught to t1, as though it were an antiderivative evaluated from here to here, which of course it is. Now that comes from an integral, so this is 1 over t1 minus t naught, the integral from t naught to t1 of the velocity dt, because s of t is, the derivative of s of t is the velocity, so the antiderivative of velocity is s of t. Look what we have then. This object on the left, which we used to call v average, is now this object on the right, 1 over t1 minus t naught, integral from t naught to t1 of the velocity. So this is average velocity in another form. Instead of just this form here, we now have this form, which involves calculus. And that should help connect this up to what we've done before. It's just a very nice result. Now, let's do an example of how one calculates this, just for some practice. And we get to practice a lot about integrals here, so this is a good example. Find f average, the average value of f, if the function f of x is equal to e to the 3x power over 1 plus e to the 6x power on the interval that goes from minus log 3 over 6 to 0. Well, before I get into finding the average value here, I like to analyze the problem to see if I understand it. So let's do a few things here. Let's look first of all at the graph of this, which you can do easily enough. If you do look at the graph, you'll get some kind of a picture like this. It turns out, well, for example, when x is 0, you have 1 over 1 plus 1, so it goes up here to a height of 1/2, which I'm going to write here as 0.5, and you'll see why. And then if you actually analyze the function, you get a curve that goes like this, symmetrically on both sides of the y-axis. The part we're looking for is from minus log 3 over 6. So let's just say that's over here somewhere, minus log 3 over 6. So here would be the area under that. That would be the definite integral. And then what is the height of the function here? Well, here that would be where I put minus log 3 over 6 into this function, and you should do that to check. You will get a number that is approximately 0.43. So if I'm looking for the average value here, that average value should be between the lowest and the highest point here, should be greater than or equal to 0.43 and less than or equal to 0.5. So this tells me where my number should be roughly. So when I find it, I'll know whether I've found an average that seems reasonable. So here's a good idea to look at the picture. There's 0. Okay. Well, the solution's easy enough. The average value is 1 over b minus a. So here that's 1 over 0 minus a minus log 3 over 6 times the integral from minus log 3 over 6 to 0 of the function which is e to the 3x over 1 plus e to the 6x dx. Now that's a little complicated, so what I'm going to do is use substitution, a method that's worthwhile practicing, to simplify this particular integrand. So let's let u be equal to e to the 3x. Then du becomes 3 times e to the 3x dx. And then that 3, when we come to the next page, we'll have to realize there's no 3 in here, so we'll have to put a 1/3 out front to compensate. We'll do that on the next page. Then I need to do the two limits. So u at the upper limit at 0 is e to the 0, which is 1. U at the lower limit, now this seems complicated, but watch what happens. Minus log 3 over 6. That's e, or minus log 3 over, over 6. And so we've got e to the 3 times that. So 3 times this will be minus log 3 over 2, because the 3 and the 6 give me 1 over 2. And that can be reinterpreted as e to the log 3 to the minus 1/2. See, the minus 1/2 can be thought of as a power multiplied out front and comes back up here due to log rules. And so e and log undo each other, and suddenly we just have 1 over the square root of 3. Now all of that should remind you of all the techniques we've tried throughout this course, and I hope you were able to pull that off. So we have now the limits, and we know that we're going to have to put a 1/3 out front. So our integral now becomes 1/3 times 6 over log 3, that's still there. Integral from 1 over the square root of 3 to 1 of 1 over 1 plus u squared du. Now that's an integral that you should recognize. This simplifies out front to be 2 over log 3. This is now the inverse tangent of u from 1 over square root of 3 to 1, which of course is 2 log 3 tangent inverse of 1 minus tangent inverse of 1 over square root of 3. We've done tangent inverse of 1 many times, so I hope you realize that that's going to be 2 over log 3 pi over 4, because that is the angle whose tangent is equal to 1. This one you may or may not remember, but if you go back to one of the triangles we often look at, the triangle where we have pi over 6 as an angle here, remember the sine of that is 1/2, which makes this third side here square root of 3. And so if we want to know what angle has tangent opposite over adjacent, well, it's exactly pi over 6. So this is pi over 4 minus pi over 6. And then this becomes pi over 6 log 3, which is approximately 0.47. And if you recall, we had numbers 0.43 on the left, 0.5 on the right. So this indeed seems to be the correct average of the function, which is what we were looking for. Now this application is one that's directly related to physics. As you can see, we're going to talk about work. First, we'll talk about the kind of work you might have seen in algebra, which is work done by a constant force. And then we'll move on to where calculus becomes necessary. So work done by a constant force, the first thing we need to make sure that we are clear on here is that in this situation here, we will assume that the force is applied in the direction of motion. If it's not applied in the direction of motion, then we have to introduce vectors. And that takes us into a branch of calculus that we haven't gotten to yet. So we'll just go in the direction of motion right now. And let us recall the definition of work you might have encountered before in your life. Work. Work, by definition, is a product of two objects. It is the product of the constant force applied in the direction of motion. So it's this constant force, and constant is very important here, times the distance the object moves in that direction. So that's what work is. It is the force times the distance in this sense. So often abbreviated W equals F times D. Now that formula again only works when the force is constant, so be careful. Later we will talk about the function, the force function being a non-constant function, and in that case this formula fails. So we need to be careful. Now let us observe that we can interpret this in the following way, and this will be helpful later. We can interpret this as a graph. We can say that if this is the force axis, and this is the distance axis, then if this is the height F, which is the constant force here, then what we have is a horizontal line for the graph of that function. And if it only goes over a certain distance here, d, say from here to here, then you see that work becomes the product of that, in this picture, becomes the area of this rectangle. So in this rectangle, this is the force distance, this is the distance, and this is the work in here. And the function at the top, force, is here big F, but later we'll want to look at functions that are more general and may not be just horizontal lines. So we'll call it f of x later. Notice that there's no calculus at this point. Calculus will only come in as soon as we get a variable function, and that will come next. We'll get to the calculus now and talk about work done by a variable force. And again, it's important to remind you that the force, in this case as in the previous case, the force is applied in the direction of motion. So it's in the direction of motion rather than not in the direction of motion, which, as I said before, requires the notion of vectors. All right, here's the idea. Remember the picture we had on the previous page. We had an axis system where this was the force axis and this was the distance axis. But now let's imagine we have a function, f of x, which is not just a constant function, so it varies in some way. And as usual, we'll go from some point A to some point B. Now this is a variable force. This is where calculus will come into play. And as we've done before, let us calculate the area of a typical rectangle here, which has width delta xk. Its height is determined by xk star. We've seen all this before. What's different here is the interpretation. The height is big F of xk star. And so this is what we get as the area of that rectangle, f of xk star, big F, times delta xk. Now, in previous cases where we were looking at area, we just say this is the area of the rectangle. It is the height times the width. But notice the values here. In this case, the function is actually a force, and this is the distance axis, so delta xk is a distance traveled. So we have force times a different distance. In other words, we have a piece of work here. So what we want to do then is do what we always do when we've started this analysis by integration. We add these all up from k equals 1 to n. Then we take the limit as the maximum value of the delta xk's goes to 0. We end up with an integral. So here again is another application. This integral is the work integral. It is the integral from a to b of the force function, big F of x dx. And in this case, we need to remind ourselves that objects move from A to B. Now in this picture, that would mean like this. From A to B is what we're thinking of the objects moving. And f of x in the direction of motion. So it's a force applied in the direction of motion. That's crucial here. With that in mind, this box now tells you how to calculate work. It is the integral of f of x dx, where f is the force. Now we will expand upon this as we go, but it's good to keep this in mind as a good starting place. Now let's do two types of examples. The first set of examples, and I'll just do actually one example here, but the whole set of examples is a set dealing with springs. That's a nice set of examples for examining work. Now springs are governed by what is called Hooke's law, a physical law that says the following. Big F of x equals k times x. So I need to tell you what all these letters mean. Big F of x, as you might guess, is a force. And what is this here? This is the force needed to restore the spring that has been either stretched or compressed x units from its natural length. Every spring, whether it's under no compression or stretching, from its natural length. Every spring has its own natural length, and then if you stretch or compress it, it moves from that natural length. So that's what this force is here. The K here is simply called the spring constant. And it varies linearly depending on the spring. If you have a very small spring, like one in a watch, for example, K will be very small. If it's a very large spring, as in a truck, for example, it'll be a larger K. What is X? X, then, are the units which can be plus or minus, because plus means stretch, minus means compression. The plus or minus units that the spring is stretched or compressed from its natural length. So those are the actual number of units, the X value here. And that's the formula known as Hooke's law. So in practice, it goes like this. Here's an example. It is a spring example. And suppose you are given the following information. You're told that a force of 5 newtons is required to stretch this spring, stretch it 1 meter beyond its natural length. We want to do 2 things with that. First of all, what we want to do is find the spring constant. That will give us a formula, a complete formula for the force here. And then we'll find work. And let's see, work to stretch it 1.8 meters beyond its natural length. So it's just a matter of doing this in order. First thing to remember is if it's a spring problem, Hooke's law applies. So it's a good thing to write it down. Hooke's law is f of x equals kx. And in part A, we're given the information that a force of 5 newtons is required to stretch it 1 meter. Well, of course, that gives us k is equal to 5 with the proper units here. Thus, we have, in this particular problem, f of x is equal to 5x. And now we can go on to answer any other question we want to ask, in this case, a question about work. So in this case, work is equal to the definite integral from a to b of the force. That's what we saw before. Now in this case, the force is 5x from Hooke's law, which we saw on the previous page. We want to know where x begins and where x ends. Well, x begins at 0 because that corresponds to the natural length of the spring. And the reason is, if it's not stretched or compressed, which is what x measures, then it has a length of 0 as far as x goes. And that just corresponds to whatever the natural length of the spring is. So it's 0 away from that natural length. And then it's plus 1.8. I don't really need to write the plus, but it's good to write that to remind ourselves that this is a stretch of 1.8 meters. Well, with all of that set up, which is really the hard part here, now we just have a very easy definite integral. This is 5x squared over 2 from 0 to 1.8. That turns out to be 8.1, and the units for work are joules. And there we go. That's all there is to that. So working with this spring sort of problem and using Hooke's law is very easy. Let's do a second work problem here that's not about springs, but it's a very nice problem anyway. This is the leaky bucket problem. So here we have a leaky bucket. And the leaky bucket weighs itself 22 newtons. Now this leaky bucket is being lifted at a constant rate. That's important here. It's lifted at a constant rate to 20 meters above ground. I'll draw a picture of this in just a moment. The rope that is being used to lift this bucket, the rope itself has weight, and the rope weighs 0.4 newtons per meter. Now here's the picture that we can draw to kind of illustrate this. Imagine we have some sort of a building here. This is the ground down here. This is the top of this building. So here's the building. And let's imagine that by some means we have a bucket suspended here. So here's our little bucket. And this little bucket is leaking. It's liquid here. Now, the distance from the ground to the top of this building is 20 meters. That's given to us. And we will say that the bucket's position at any point in time will be x meters. So we'll just write x there. Okay, so we're back here. The rope weighs 0.4 newtons per meter. We want the bucket to start with 70 newtons worth of water. And we want to say that it leaks. It's not only being lifted at a constant rate, but it leaks at a constant rate. If these rates are not constant, that causes the problem to be more complicated and one that could be dealt with later calculus, but not here. The bucket also just empties when it reaches the top. So the question is, what work is done in lifting up this bucket? Now, to analyze this, we need to understand that the total work done is actually in 3 parts. There's the lifting of the metal bucket, say, or the wooden bucket itself, which doesn't change in its weight from top to bottom. So that has to be taken care of. The second thing is there's the water, but the water is constantly changing in its amount because it's dripping out. Also, the rope has to be lifted, but as you go higher and higher, there's less and less rope. So that's changing. And because of all this change, that's why calculus is being used here. So the total work will be the work to lift the bucket plus the work to lift the water plus the work to lift the rope. And we'll actually do it in that order. So let's do the easy one first, which is the bucket. In this case, no calculus is required because this is a constant force. The work is equal to the weight of the bucket. That's the constant force I was talking about, 22 newtons. So that's a constant force here, times 20 meters, which is the full distance it travels, and that gives us in the end 440 joules. No calculus required if the force is constant. Now let's deal with the water and then with the rope, both of which are changing over time, so force is not constant and therefore calculus is required. So let's see what the force is here. The force is some proportion of the amount of water, which was the constant force of water that we started with. It's some proportion of that. At any given position, there's only so much water left. So this is 70 newtons, and this is the starting weight of water, start weight of the water. And weight, of course, is another word for force here. Then what we need is a proportion of the water that remains at any given position of the bucket. Well, that proportion can easily be calculated as 20 minus x over x. This is how much is left out of how much you've already traveled. This should be 20 down here. Sorry. This is how much is left over how much is to be traveled, which is 20. And this is then the proportion I mentioned. So this is the proportion of water remaining at height x. So that's how much there is remaining because that's how much there is to go in distance over the total distance. And that's 70 minus 3.5x. So again, this integral, this work integral is very easy. The work becomes the integral from where x begins, which is 0 on the ground, to 20 where it stops, of 70 minus 3.5x dx. And in the end, this becomes 700 joules. That's a very easy calculation. You can do that yourself. And then finally we have the rope. And the rope has a force, well, it's 0.4 newtons per meter, and the amount of rope remaining at any point is 20 minus x meters. So that means the work is going to be where x begins and ends is 0 to 20 of 0.4 20 minus x, and again this one's easy, dx. This turns out to be 80 joules. So you add them all together and you get the total work involved here, which is 1,220 joules. So that's all there is to it when we're doing work problems of this sort. This is the most interesting application of work of all, and it really depends on your understanding how integrals are constructed. This is called do-it-yourself integrals, pumping fluids. We will do this by example. And here is the situation. This could be any kind of a tank, but let's suppose we have a conical tank. as shown. We have a tank that looks something like this. It's a big cone, and I can dot in the back side maybe to show you. And what we have is a hole at the top of this conical tank. And what we want to do is pump all the liquid in the tank out of the hole. Now let me give you some more information here. Let's imagine that we put an axis system on here so we can keep track. There's a horizontal axis. Let's draw a vertical one here. Let us say that the tank itself is 30 feet tall. And let's suppose that in here there are 15 feet of water. So this is 15 feet of water. So this in here is water. What we want to do is take this water and pump it out of the top where there's a hole. And the question is, how much work is involved in doing that? And work is important because, for example, we might want to use a pump which has a certain horsepower to pump the water out. And that, knowing how much work it will require, will tell us what size horsepower pump we need to buy and how long it will have to work. So one other dimension we need to have here, the radius of the base of the cone, we'll say is 10 feet. Now, to organize this, what you can do is imagine that you've got a vertical axis here, like so. And let me write that down here, vertical axis. And let's say this is the 0 height. We're going to do it in a reverse direction. Seems counterintuitive, but it really works out pretty well here. 0, and then here will be a height of 15, and here will be a height or a depth, if you like, of 30. So either way you can think about this, maybe depth would be a better way. We have 15 and then 30, and the water is in this part here. What we want to do here, the question is, find the work to pump the water up through the hole. So that's what we want to do here. Now you may say, well, this looks hard because we have to figure out how to pump something that is fluid in nature. But you know, we've done this kind of argument before. If we're dealing with the fluid, what we'll do is use our notions of calculus to help us think of the fluid as really coming in chunks that are in the shape of disks. And we'll lift it out disk by disk. So here's the solution, and here's again where the power of the calculus comes in. We will lift the water out, theoretically, as disks, and that will allow us to do it in practice. So what we'll have here is a disk like this, oriented horizontally, of course. It will have a height of delta xk because we have an x-axis going this way. This position of the disk at an arbitrary position will be on that axis at some xk star position. So up here was the 0. Here's the xk star position, the arbitrary position. And the radius of the disk we'll call r sub k because we'll need to work this out. So the thickness of the disk and the radius is necessary, so we can find the cross-sectional area, which of course is a circle. So how am I going to find r? Well, if we observe back at the cone and we slice it vertically, we'll see that we can have a slice that looks something like this. And that if this is the height where RK is, and this is the base of the cone, so this is 10 feet, then we have some other dimensions we can mark. This dimension here is xk star, because we're measuring from the top down. And then the total distance, of course, is 30 for the entire cone. So with these two nested similar triangles, as we've done before, we can find RK. Let's see, RK is to 10, this side is to this side, as xk star is to 30. That's this side is to this side. And now we can just solve for RK and get 1/3 xk star. So there's my RK. With RK, I can write the cross-sectional area of the disk, multiply it by the height, and get the volume. What will that do for me? Well, watch. We'll have the kth volume of the disk, or the volume of the kth disk, if you like. And what is that? The cross-sectional area, which is pi r squared. Here's r, so it's 1/3 xk star squared, times, so there's the cross-sectional area, times the thickness, which is delta xk. Then once I have the volume, I can move to the next step and get the force, which in this case is the weight. So the kth force on the disk becomes the volume, and I'll multiply all this together. Let's see if I can simplify a bit here. I've got pi, 1/3 squared is pi over 9, so I'll write that. Then I've got xk star squared, and then I'll put the delta xk. So there's the volume repeated, times rho, and we'll let the letter rho mean the weight density of water here. So the weight density of water. So this will give us the force, or the weight, if you like, on that kth disk. Now we just need to get the work in the kth case. And so the kth work on that disk, let's see, that was force through a distance. So the kth force will be multiplied by the distance that that disk is going to travel. The kth force we had from the previous page was pi over 9. I'll put the rho here. Xk star squared delta xk. So that's just the force we calculated. And the distance is going to be the distance that the disk has to travel upward to get out of the cone. That's from xk star back up to 0. That total distance is just xk star. So once we have the kth version of the work, we can go immediately to the integral. This is the do-it-yourself part. We have built our way up to the integrand. This is now going to be the integral from, let's see, where does the xk start and end? Well, as we're going down the axis, remember, this way, there was a 15 and a 30. This is where the water was in here. So going downward from 0, 15 to 30 will tell us where the water is. And then putting all of this in here, we have pi over 9 rho. There are 3 xk stars, so that becomes x cubed, and then the delta xk becomes dx. This integral at this point is an easy integral. What was hard was setting this up. And if you follow the process we showed above, you'll be able to do it yourself and set up your own integrals. Once you get to this stage, the rest is easy. You'll get an integral that, if you work it out, will give you something like pi over 36 times rho 30 to the 4th minus 15 to the 4th. And if rho, weight density for water, is taken to be approximately 62.4 pounds per foot cubed, you can always look that up in a physics book, then what you get here is that the work is approximately 4,135,000 foot-pounds. So that's quite a lot of work, but then again, that's quite a lot of water, and that's how you do it yourself. As one more excursion into physics, what we'll do is we'll derive what's called the work-energy relationship, where work is change in kinetic energy. Now, to set this up, to make sure we have all of our assumptions in one place, let's write them all down. We will imagine that we have an object that moves over some x interval, AB. So what we're talking about is a situation where here's A and here's B, and the object or the particle is moving in that direction. Now, as always in these problems, our force, because we're not dealing with vectors yet, our force is applied in the direction of motion. So in the direction of motion. So that's the second assumption. The next are going to be notational conventions. We'll let x be x of t, and that will represent the position of the object. That seems reasonable. And that, of course, is the position of the object at time t. So t stands for time. So when we go from time t0 to time t1, say, then the interval AB can be rewritten as the interval going from x of t0 to x of t1, because A is the initial position, and that happens at the initial time. So A is x of t0, B is the final position at the final time, x of t1. Then we'll continue here. V will be v of t, that will be the velocity, and of course that's x prime of t, the derivative of the position function. And then v prime of t is the acceleration. And finally, the letter m, the small m, will be the mass of the object. So those are our assumptions about the notation and what we mean about the force here. Now let's write down one fact that we'll have to use, which is Newton's second law of motion. Newton's second law says that the force F of x, or F of x of t, is equal to the mass times the acceleration, which I can write as v prime of t, because acceleration here was v prime of t. So, with that as the setup, we're now going to write down work and then interpret it as a change in kinetic energy. So we'll have to come up with kinetic energy at one point. So here is the work in this situation. It's the integral from a to b of the force, f of x dx. That we've seen before. Now let's start making some change of variable. Let's let x be written as x of t, position function. Then dx becomes x prime of t dt. But of course x prime of t is v of t dt, the velocity. The upper limit will be x of t1, which is b. The lower limit will now be x of t naught, which is a, and so that will give me the values for t in the next integral. So this now becomes the integral from t naught to t1 of f of x, which is now x of t. Dx is all of this, so dx is v of t dt. So there's the dx. Now I will use Newton's second law, which we saw on the previous page, to translate this function into something involving velocity, because I have a velocity here, so that will be good. So t naught to t1. Newton's second law says the force is equal to the mass times the acceleration, which is the derivative of the velocity, and then I'll just bring down the v of t dt. And now I will go ahead and do another change of variable. I will write v of t as v, for short. Then dv becomes v prime of t dt. That's nice because I have a v prime of t dt here. Then the upper limit will be v of t1, and that we will rewrite as vf, and that will stand for f for final. And this is final velocity. And then the lower limit will be v of t naught, which will be v sub I, and the I stands for initial velocity. So a little notation change there as we do this translation box. Continuing on down, we now have the integral that goes from vi, the initial velocity, to vf, the final velocity. The inside just becomes mv dv. Well, that's an easy integral. It's going to be mv squared over 2. So this becomes mv squared over 2 evaluated from vi, the initial velocity, to vf, the final velocity. Putting the upper minus the lower in, we get 1/2 m vf squared minus 1/2 m vi squared. And that is what we were trying to get to. Let's write this down in one place. This is called the work-energy relationship. And what it says is that work is equal to this 1/2 m final velocity squared minus 1/2 m initial velocity squared. That is the work-energy relationship, because this first expression is what's called the final kinetic energy, energy of motion. And this expression is the initial kinetic energy. And that is also energy of motion, and of course the difference is the change in kinetic energy from the start of when the work began to the end. So there's a nice derivation of a well-known physics formula using the calculus, showing the power of the calculus here.